at Developing Concepts of Decimals and Percents, largely taken from John Vandewall's teaching Elementary and Middle School Mathematics, Chapter 16. So that'll be our goal. We're going to spend a little bit of time just thinking about, the introduction of decimals, coming after the learning of fractions, and then thinking about how to compute with decimals, and transitioning a bit then to working with percents will be the flow of today's video. So let's jump right in. I think to start, it'd be good to grab a piece of paper and just take a few minutes and work out these 4 questions just to activate your prior knowledge and think about your current thinking about decimals. So go ahead and pause the video and try these 4 questions. All right, well, let's just check and see how you did here. So here are the answers on the bottom of the screen. And, throughout today's video, we just want to take some concepts like this, and again, as usual, try and infuse it with some reasoning and sense making to really think, what really are decimals? How can they be understood? What are some conceptual ways of developing that understanding? And again, focus on visuals as well along the way. And with some of these here, even like number 4, you might have done it using certain algorithms, which is great, but we want to think about a little more of starting with, again, sense making instead of rules would be our goal. So one of the questions there was about the center of the decimals place. And just want to point out that one thing as teachers here to think about is that, the ones place is the center of the decimal system, not the decimal points. I remember teaching kids often, and they often wondered where the oneths place was. We have tens and tenths and hundredths, but where's the oneths? And it makes sense there is no oneths because the ones are our whole. Just like in fractions, we always define the whole. Everything begins in the ones place. And as we move left, obviously we keep kind of multiplying by 10. And as we move right, we're getting smaller. We're dividing by 10. So the whole decimal system is built around the ones place, focusing on our whole and defining our whole. And the decimal point, separates out our wholes from our decimal numbers there. But let's think about this. Let's start a little more from the beginning here and think about what grade typically introduces decimals. Well, if you were thinking 4th grade, you're right. Here we see one of the first Common Core standards around decimals, where it says express a fraction with denominator 10 as an equivalent fraction with denominator 100, and use this technique to add 2 fractions with respective denominators 10 and 100. Now, if you think about that, you might say, wait, there's no decimals in there. And in one sense, you're correct. Decimals build on our knowledge of fractions, and so this is that connection. As teachers, we need to make sure that we really emphasize and help kids to grasp. So what the standards does is starts kids working with, like often called, decimal fractions. Fractions that have denominators of 10 and 100, or maybe eventually 1,000, because that's what decimals are. In a base 10 system, we're dealing with tenths and hundredths and thousandths. So like, for example, this standard here, we see kids working on things like this. These are base 10 or decimal fractions, and just getting used to adding these up. We're not using decimals yet, but just getting used to even to the language of 4 tenths plus 30 hundredths. One visual we see a lot when we're dealing with base 10 or decimal fractions is going back to our grids. Our base 10, our 100 grids, hundredths grids to look like that. So here we might see a visual of 4 tenths plus 30 hundredths. And at this point, we've already been learning about the same size pieces and common denominators. We can visualize it and see that that'd be the same as 70 hundredths. And we start building this notion of how we add tenths and hundredths. And again, if we're taking a look at a similar problem, we might see kids working on this, dealing with what does that look like? What does that mean? And again, as a visual, we can take a look at using hundredths grid, which is a helpful visual. On the left, we see that would be 7 of the 100, so 7 hundredths. On the right, again, 6 tenths out of 100, we can realize again that that'd be 60 out of 100. So again, as we put these together and using some common denominator type strategies, we get the answer of 67 hundredths. And again, I want to make a note that we're not writing decimals right away, but we are speaking decimal language and really thinking about it in terms of fractions, because that's the connection. Now, with that, obviously we want to introduce decimal notation. And so in the standards in 4th grade, we see standards like this. Use decimal notation for fractions with denominators of 10 or 100. For example, being able to understand that 62 hundredths is the same as 0.62. and start thinking about a new notation of writing the same thing we've been saying. So one way of doing that is working with manipulatives, or dealing with some concrete visuals that we could look at. And since we're dealing with our base 10 number system, well, let's go back and think about how we could use things we've already been using in the past to emphasize this decimal notation. So let's use our base 10 blocks to think about that. So the key thing here is to redefine our whole. In the past, when we did base 10 blocks, our one or our single was always the small little cube. But we can change the whole and have it be anything we want. For example, often in fourth grade, the common way of doing that is that the flat will always be the whole, and we'll see why in a second. But let's suppose that flat, the yellow manipulative on the screen there, that's our 100 flat. And I like to give a context. So I like to say it represents one whole garden or something like that. Because if that's one whole garden, we can start thinking about fractions like, what would 4/100ths of the garden look like? For example, if I grew tomatoes in 4/100ths of that garden, how much would that be? And if we think about it, if we divide it into 100 little pieces, I'm sorry. So let's start with 3/10. So let's look at what 3/10 of the garden would look like. If we grew 3/10 of the garden, and so that was, tomatoes, well, then the visual on the screen there are our 10 rods, end up being tenths because they're each 1/10 of the whole. And now we have a visual for tenths. And if I wanted to grow jalapenos on 4/100ths of the garden, well, again, if we divide that into 100 pieces, each one of our single cubes would now be 100th. So that would be our 4/100ths of the garden for jalapenos. And if 27/100ths, is going to be green beans, can you picture what that would look like? Yeah, it would be possibly something like this. Now, you could also just have 27 of the single hundredths, but again, we could trade in, and we could trade in 10/100ths for tenths. And here we see what that would look like as part of the garden. And so it's just a visual, again, way of seeing what does 27/100ths look like. And it all depends on defining a clear whole. Now in fourth grade, that's really the basis we go on. We stick with tenths and hundredths. But later on, when we get to thousandths, we can redefine the whole as well to be that large cube. And if we wanted to extend the visual, if we let that be our large cube, and one context I like to use is having a whole big block of cheese, like a big block of cheddar cheese. So can you imagine now what 3/10 of that block of cheese would look like? Which piece would be our tenth? Well, yeah, a single flat piece, 100th flat, it takes 10 of those to make a large cube, so each of those represents a tenth. So that would be 3/10 of the block of cheese. What would 4/1000ths of that cheese block look like? Well, if we divide it into 1,000 little pieces, that would be our single little cube. So that's what 4/1000ths would look like. And if we're getting real precise and want 273,000ths, well, let's think about that. We might have, so we'd have 2 of the tenths, 7 of the hundredths, and 3 of the thousandths. So again, as we define our whole, all the other pieces take on new meanings. In this case, we see what that would look like for the large cube. Well, when making the connections to writing decimal numbers, let's go back to, again, tools we've used in the past, like place value mats. A place value mat, in this case we have a decimal mat, can be a great way to make connections between the written numbers and the values of what we're looking at. So for example, let's take a look at 2 and 3/10. And let's use it as this place value mat looks at. The ones place is going to be our flat, so like our garden analogy here. So if we started with this place value mat and we asked kids to show us 2 and 3/10 gardens, well, on the mat, it might look something like that, correct? That would be 2 whole gardens and 3/10 of a garden. But using a place value mat, we can see that there's this, a nice way to write this using decimals. Is we use the decimal to separate the whole gardens from the partial gardens. Again, seeing 2.3 is just a much, more efficient way to write that same amount, 2 and 3/10. In the beginning, it's very important to think about, I know we have been using decimals for a while, we say 2.3, that's just the way we say it, but in the beginning, it's real important to emphasize the meaning. This would be 2 and 3/10, to really emphasize the meaning of what we're saying and not rely on the shorthand knowledge of 2.3. So let's take a look at this one. What would 1 and 12/100ths look like? Can you picture it? Well, actually, there's a couple ways you could picture it, right? I mean, for example, we could imagine this on the mat. Would this be correct? Yeah, sure, this is one whole garden and 12 hundredths of a garden, and that would be correct. Now, one thing we learned just back when we did with blocks before is that when we want to write numbers, we want to do it in efficient ways, and so if we can make a trade, we want to make a trade, just like we did with base 10 blocks in the past. So, yeah, can we trade in 10 of those hundredths for one of our tenths? Well, sure, that's a trade we could make. So if we make that trade, it might look more like this. Yeah, still the same amount of gardens. We have, still the same amount, but we're just trading up for the bigger pieces that we have, and this would be no more trades could be done. So if we're going to name it more efficiently, we can see that this is how it would look like using decimal notation. We have one whole and 1/10 and 2 hundredths. Or we could name it 1 and 12 hundredths. And again, a note on naming decimals is it's totally fine to say 1 and 1/10 and 2 hundredths. That would be base 10 language around decimals. Now, the standard way of saying it is 1 and 12 hundredths, and that's fine. And the standard way is we always basically imagine kind of trading in for the smallest piece, kind of like we saw here, which is kind of funny. That's actually, reading it in standard form, it looks like that, 1 and 12 hundredths. So just the smallest piece is the standard way of reading it in terms of that's what we would get if we traded in for all those small pieces. Yeah. So if we looked at, this one, like, 3 and 12 hundredths, what could that look like? This is one way it could look like. And again, as we emphasize it, in base 10 language, we could say 3 and 1/10 and 2 hundredths, or using standard language, 3 and 12 hundredths. So again, both are fine, both have a place, and we see how the visual connects to the written and oral language for decimals here. So for you, let's change it up for a second. Let's suppose our whole now is defined to be a large cube, going back to like our large block of cheese. How would you say this number? How would you write this number? Would you pause the video for a second and think about what this number would be, this represented both orally and in written notation? All right, well, if that large block is our whole, then the sticks here represent, each of it would take 100 of those to make the large block. So those sticks are actually hundredths of that block of cheese, and the little cubes would take 1,000 of those, so those are thousandths. So if we look at it in terms of written notation, it would be like that, 2.046. We don't have any of the tenths, which would be the flats. And we could read this a couple ways. In standard language, we would say 2 and 46 thousandths, always reading it in terms of the smallest decimal value, as if we had traded in for those smallest values. Or, in base 10 language, 2 wholes and 4 hundredths and 6 thousandths. And that would be the way for that. Now, as we get into decimals, other things we come across is being able to compare decimals, right? And think about that. So here's a standard from 4th grade about comparing two decimals to hundredths by reasoning about their size and using visual models and other reasoning strategies to go through. So yeah, let's think about that for a second. So comparing some decimals. So here's some things you might do right now, even for yourself. Think about which is larger, that one on the left or the one on the right. In each case, what would it be? Now, for part A there, if you're following along with me here, as people who've been through this a lot, we may already realize that, well, the 4/10 is larger. But can you imagine how that's confusing for kids? Because when they first see it, they see a 36 and they see a 4. And they know that 36 is more than 4, yet now we're saying that the one with the 4 is actually bigger. So that's where, without some deeper understanding, we can see how a lot of misconceptions could happen when looking at something like comparing those two right there. So let's think about that. Well, let's think of, again, when we're confused, often we can think of how a visual may help to think about it here. So, for example, let's start with that being our whole, and for 36 hundredths, we might look at it like that. So 3/10 and 6 hundredths. And the second one, we know that's saying 4/10. So here, if you think about it in terms of a garden, we can visually see that, right, 4/10 is more than the 36 hundredths, right? That would be more of the garden doing that. And so visually, just knowing, having something to base what these mean helps us see which is more. We also realize that, as the yellow box indicates on there, that when you're comparing decimals, well, remember, these are fractions. When you compare fractions, a great way to do that was having a common denominator. So with decimals, to get a common denominator, so to speak, it's just looking at it with the same number of places. So, in this case, if we looked at 2 decimal places to the hundredths, if we just add in that 0 on the 4, we see we could also think of it, instead of 4/10ths, it would be equivalent as 40 hundredths, same number. And if we see 40 hundredths and 36 hundredths, well, that actually makes a nice way to compare it as well, because we know 40 is more than 36, and now we're comparing the same size pieces. So it makes it just even easier to see that, well, 40 hundredths, of course, is more than 36 hundredths. We have more of those pieces. And the other visual, besides base 10 blocks, that you'll see in schools a lot is, again, going back to those hundredths grids. And again, here we can see that on the left side, and that's what 36 hundredths would look like. On the right side, that's 4/10ths or 40 hundredths. And again, we can see how the 4/10ths or 40 hundredths is more visually than the 36 hundredths. So again, it's helpful to build understanding using visuals and context, as always, to make sense of what we're doing here. And that's important to think about in those past examples, to think about equivalent decimals, equivalent decimal numbers. Just like there was many ways to write equivalent fractions, 1/2, 2/4, 3/6, 4/8. With decimals, there's lots of ways as well. For example, all these are equivalent, right? We start with 2/10ths, and if we just add a 0 in a hundredths place, we're not adding anything. Adding 0 hundredths to it is nothing, so that's the same amount, but we could say it's 20 hundredths. Or adding a 0 in the hundredth spot, the thousandth spot, is still adding nothing, so it's the same. It's 200 thousandths. And this is another big idea of equivalence that can be helpful when we just are comparing and thinking about computations here coming up. Equivalent decimal representations here. Now, so far we've been dealing with, numbers that had denominators mostly of 10 and hundreds, so we can think about it more easily in terms of decimal numbers. But of course, all fractions can be turned into decimals. And so let's think about some strategies here that we see to do that, and you'll be using in this week's problem set. So we take a look at, like, for example, 3/20ths. One example is often where kids start is turning anything into a base 10 fraction when possible. Since decimals are out of tenths and hundredths, we could think, well, what could we do with 3/20ths? Could we write an equivalent fraction that's out of 100 or out of 10? And sure, and in this case, if we multiply by a giant 1 of 5/5, we can see that we would get the equivalent fraction of 15 hundredths. And if we understand our decimal notation, that the fraction 15 hundredths, well, decimal is the same thing. We can write it as 0.15, 15 hundredths, same thing. And again, this can work nicely for a lot of fractions now, definitely not all though, but again, conceptually, often students will work with numbers that work well. So you could think of how we could do that with 3/4. Or a number like 9/15. We might have to simplify that fraction first, right? 9/15 would simplify to 3/5. And from there, we might multiply by 2/2 and get that to 6/10. And realize again that would be 6/10 or 0.6. Now, not all numbers will go nicely into a common denominator of 10 or 100 or 1,000. So, of course, we need to think about other things like 1/8. What is that going to entail right there? So let's take a look real quick and just review, as teachers here, that aspect of if we have a fraction like 1/8, how we're going to think about the decimal equivalent here. And one strategy that always works is, again, using some form of division or long division to wonder, okay, well, I have 1 divided by 8, so again, I'm wondering, how many 8s go into 1? Well, definitely not any of them, not any whole of them. We'll have to cut that 8 into smaller parts. And again, using language before, we could think about something like if I had 1 pound of that cheese from earlier, and we're sharing it between 8 people, how many pounds would each person get? So it's the same context for division as before, 1 pound shared between 8 people. Now, the only thing is here is we know that they won't get a pound. I'm going to need some smaller pieces of tenths and hundredths and so on. So I'm going to use the decimal point to just put in some zeros. It really doesn't matter how many we start with, but we're just thinking of smaller pieces, right? This is our whole, and this one here is going to be our tenths, and this one here is going to be our hundredths. And if it's helpful, like before, we can even draw in our place value columns like before. And realize again, so if I'm dealing this in terms of, I can't give the wholes out, so in terms of the tens, it would go in there one time. And for the decimal, I'm just going to put the decimal here right now. It's going to be stay in the same spot, so we're just going to bring it up. So each person would get a tenth, which means I gave away 8 of those tenths, and there'd be 2 tenths left. Not enough to share with 8 people, so I could trade it in, bring down the 0, which basically means 20 hundredths. Each of the 8 people could get 2 of those, right? Which means I would give away 16 of those hundredths. So left with 4. Not enough to give to 8 people. So if I wanted, I could go over to thousandths, right? And bring in the next column here for thousandths. Sorry, my writing here is a little messy here. And when I bring that down, it's like trading in for 40 thousandths. Oh, if I did that between 8 people, that would be nice. They would each get 5. And oh, that worked out nicely here. So like 1 pound shared with 8 people means each person would get 125 thousandths of a pound of cheese, or 0.125, or 1/10, 200ths, 5 thousandths. So again, just talking through that, we see how the same principles apply to division from earlier. And of course, we can turn any fraction into a decimal using that. All right, let's bring it back up again. So when we think about computation with decimals, starting to add, subtract, multiply, and divide, let's just take a look at that a little bit here today to think about that. And here we see in 5th grade standards, we see things like this: add, subtract, multiply, and divide decimals to hundredths using concrete models or drawings and strategies based on place value and so on. But again, we see here this notion of models and drawings and strategies using place value. And we start thinking about it. Again, there's lots of misconceptions with decimals that we may run into. When you look at this on the screen here, I mean, what mistake is made here, and why is that a mistake? Looking at that, you're probably saying, well, hey, this student didn't line up their decimal spots. Yeah, well, but why do we have to line up decimal spots? Well, because when we add up, we're basically adding likes with likes, adding up the same size pieces, right? Just like with fractions, when we added, we needed common denominators. Decimals are the same thing. Decimals are fractions. So we have to make sure we're lining up tenths with tenths, hundredths with hundredths, and so on. So we're adding the same size pieces, which this example would violate that right here. So let's take a look at one example, all right? I mean, for problems on the right, you see some basic addition and subtraction decimal questions here. Again, we can begin with estimation, just like in the past lessons we've been learning. Is just start with a thought. If you have the 2 and 35 hundredths plus 1 and 86 hundredths, we might think about this. I mean, what's this answer going to be close to? Is this answer going to be, more than 10, less than 10? More than 3, less than 3? Just again, asking those benchmark estimation questions pauses and makes us think about what a reasonable answer might be near. Like this one looks like it should probably be near about 4. We already have 3 wholes and we have a lot of decimals there, so it should be near 4. Would be a great thing if students could even realize the answer should be around 4 before we start. And let's think about some visuals here with base 10 blocks or other things and story problems. It's just like in the past. So let's take a look at that first one. 2 and 35 hundredths plus 1 and 86 hundredths. Again, I mean, we could make up lots of story problems to have this make sense of this. I've been shopping recently for some groceries and had to get some meat at the grocery store, so I made up this one. Sierra bought 2 and 35 hundredths pounds of chicken and 1 and 86 hundredths pounds of beef. How many total pounds of meat did she buy? Again, estimation. What do you think? More than 5 pounds? Less than 5 pounds? More than 3 pounds? Less than 3 pounds? So again, we can start with questions like that. And if we're going to use manipulatives to think about this, we need to always define our whole. So let's let the flat be our pound. And if that's a pound, I think we could agree that this is what 2 and 35 hundredths pounds of chicken would look like. And this is what 1 and 86 pounds of beef would look like. So if we wanted to actually, look at it visually, again, we'd have to make trades, as we always do. If we look at the hundredths pieces, can we make a trade? Yeah, look at the small pieces, and if we were to trade it in, we would get that. We have enough to trade in for 1 of the tenths. Yeah, so great. So now we have lots of tenths. Could we trade those in? Yeah, we could. So if we do that, oh yeah, we have enough to trade in for a 1 whole pound with 2 tenths left over. And if we just scoot that whole over, we would see with the blocks that we would end up with 4 whole pounds, 2 tenths, and 3 hundredths. Written as 4.23. Yeah, and so again, we just see that, going through there, and if we were to, again, use the common algorithm, we could just line up those numbers, the decimal point, and add and regroup as we normally would to get the same answer. So that's the same. Addition and subtraction really works the same as we did before. We just have to use that language, base 10 language, as we go through, and we see that. So let's take a look at multiplication for a little bit. And same thing, we want to think about estimation. And here, with multiplication, when working with whole numbers, we often dealt with groups of, like 3 groups of 2. So like this problem here, if we have 3.5 times 0.4, we can think about it in terms of groups. 3.5 groups of 4 tenths, or area as well can be a nice one to think about as well. So let's look at this one for a second. Let's take a look at that question, and let's take a look at a silly problem here about Sabrina the speedy snail, who can travel 4 tenths of a foot every hour. And if she was exercising for 3.5 hours, how far did she go? How many feet did she go? Well, again, let's start with estimation. So what do you think? Do you think she went more than a foot or less than a foot? That would be a good question to start with, and we'd have to think about that and talk with our students. Do you think she went more than 10 feet, less than 10 feet? Do you think she, just those kind of questions to go through. And if we can reason out that, 4 tenths of a foot's close to a half, right? And she went 3.5 hours, that definitely would go more than a foot then. And even just realizing that would be a great place to start. So let's take a look at this. There's lots of ways we could look at this with base 10 blocks or number lines to go through and to think about that. So let's take a look at a few things with that. Let's start with base 10 blocks, and then we'll move on to number lines here. So I'm going to grab my base 10 blocks over here on the table. Give me 1 second to grab these and pull these up out of my bag here. And I guess I need to share my screen. So let me go ahead and do that. All right, so share my screen here. All right, good. So we're going to look at 3 and 5 tenths times 4 tenths, or 3.5 groups of 4 tenths. So again, if we look at it in terms of a model, what we need to do is define our whole again, so we know what that would be. So again, what I'm going to do here is I want to go ahead and just define the flat here to be my whole. And the question is, what would this be? Now again, we're looking at 3.5 hours of 4 tenths of a foot. And our answer is going to be how many feet did she travel. So our answer defines what we're going to have as our whole. So this here would be 1 equals 1 foot. And we want 3.5 groups of these, right? So let's take a look. So let's take a look at what we'd have. So in 1 hour, we know we didn't go a whole foot. We went 4 tenths of a foot. So each of these would be a tenth, right? So this would represent 4 tenths. So after 1 hour, I'm going to use just the stick notation to have that be 4 tenths. And, another hour. And so the second hour, she would go another 4 tenths. And she did a whole third hour. She had a big exercise today. She did another one, right? And then when we get to the last half hour, she did that half hour. Well, what would a half hour be? Well, it would be half of our 4 tenths of a foot, right? So it would be 2 of those tenths. So visually, this is 3.5 groups of 4 tenths, right? 3 full groups here and a half a group of the 4/10 there. And then we could do some trading, right? We know that it would take 10 of those tenths to make a foot, and we'd have we'd have 4 of those tenths left over. So that's 1 4/10 feet is how far Sabrina would have gone. Yeah, so we see that model like that. Now, a number line can be a great way as well to think about this. So just visuals here to go through. In fact, a number line may be even more intuitive when you think about it. I'm going to go ahead and look at, so I'm going to divide our number line up into tenths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so here I have a number line that's going by tenths. And so here we might imagine this, just after 1 hour, right, that would be 4/10 of a way to 1 foot. And after another hour, that would be another 4/10. After another hour, that would give us 3 hours is there. And now we have that half hour, right? And a half hour would be half of what we jumped previously. So it would get us right there. So that's 1, 2, 3, 4. That would be 1 full foot and 4/10 of the next foot. So again, we see, 2 different visual ways to think about 3.5 groups of 4/10. And if we were to look at this with the algorithm, right, just to think about if we were to write this out as 3.5 times 4/10, again, different ways to think about it, but one way to think about it is just to realize that when we are multiplying with decimals, like common with algorithms, is to realize this is really, the process is no different than 35 times 4. So often, a good way to do this is to start by ignoring the decimals and not worry about them. Just multiply like we normally would using any method that we've learned. And if I use kind of the standard multiplication algorithm, I would realize that here I would get 140. But the question is, where does the decimal go? Well, so over here, where's the decimal go? Well, again, go back to estimation. Before, we realized that this should be more than a foot, but probably less than 2 feet. So when I place the decimal, the only place that would make sense would be right there. That would give us an answer between 1 and 2. So estimation alone can tell us where to place the decimal place. Yes, there's other rules as well. I mean, up here, if we think about it this way, there's basically 2 decimal places over that we ignored. So in the end, we need to put it back in. That's a helpful thing, but I always go back to estimation as more based on the reasoning and sense making there to go through. So there's an example of what multiplication could look like as we go through. Let's take a look at one more, though. I mean, some of these can be a little bit tricky, so let's take a look at one more. I'm going to make fun of my friend Brad here. And suppose that Brad was serving blue cheese, and 1 serving of blue cheese was 1 4/10 ounces. All right, so that's our approved serving of blue cheese. And Brad ate 2 1/10 total servings. Now, again, problems like this aren't really a real-world problem. It just gives us a context, right, for which to think about these numbers. So, again, the context is important here to think about. How many ounces did he eat? Yeah, did he eat, what do you think? Did he eat more than 2 ounces? Did he eat less than 2 ounces? So, well, we know we had 2 servings. Each serving was 1 4/10 ounces. So, yeah, definitely more than 2 ounces. I think he had more than 5 ounces. Again, just those estimation questions can start there. So let's take a look at this one, which is a little bit trickier, I think. So let's take a look. I'm going to go ahead and bring up this again and do this one together just to think about it. So we have, oops, sorry, wrong thing. Let's bring up that. There we go. So we have 2.1 servings and ounces here. So again, if we define something to be our whole, in the end, we're wondering how many ounces he ate. So define our whole, that would be 1 ounce in the end. So if I was going to do, our first serving here using base 10 blocks, what that would look like, well, Well, I know he had 1 ounce, so that would be one of those, and he had 4/10 of an ounce. So, well, yeah, so these would be, again, tenths of that again. So that would look like that. And he had 2 servings, right? So in the second serving, it would be another one of those. So that represents another 1.4 ounces of the blue cheese. But then the tricky thing here, what do we do with this 1/10 of a serving, right? So that's what we need to think about here, to think about what would 1/10 of a serving be of this. And again, one way to think about this is well, 1/10 of a serving would be dividing this by 10, right? So you can think about it like this. What is 1/10 of this piece? Wouldn't it be one of these? Yeah, this is 1/10 of that. And what is 1/10 of each of these over here? Well, each of these can be broken down into 10 pieces, and just to lay it on top, if I put those on top there, that would be 1/10 of each. So to take 1/10 of a serving would be, just thinking about one way to think is taking 1/10 of each piece, and that would give us these right here. It's even blue for blue cheese. And so that 1/10 of a serving would look like this, literally, to go through. Now, what are these pieces here? It's good to make a key. In your problem set this week, if you're doing this, make a key. So if that's 1 ounce, then in my drawing, then that would be 1/10 of an ounce. So what are these little pieces here? Well, those were actually 1/100th of our ounce, right? So those little ones are 1/100th of an ounce, and now we have a full key for our drawing. So if we were to group this back together here and to think about it, what do we have? Well, I have 2 whole pounds, I have 9/10, and I have 4 of the hundredths. So that's, I said pounds a lot, I'm sorry. It should be ounces of blue cheese. So let's see if we can verify it. Let's take a look at our algorithm here and just see if that visual actually did give us the correct answer and see what we get. Now again, to multiply it, I recommend just ignore those decimal places. All right, just pretend let's 21 times 14 and use any method we want here. 1 times 4 is 4, 2 times 4 is 8. If we're going over there, that would be a 10, so I'll put the 0 there for the placeholder. And multiplying that by 1 would give me that. And if I add it up, 21 times 14 would be 294, but where's the decimal place go? Again, going back to estimation in the beginning, we said we knew he had more than 2 ounces, weren't sure if it was close to 3, but again, the only place it would make sense would be to go right there. Or again, using the rule, we know that we basically ignored 2 decimal places, and so that would be right there. But again, we see just a visual representation of what the groups of model might look like, and going with the algorithm to think about that going through. Great. All right. So that's the big idea there. It's just really estimation. If we are looking at any type of decimal multiplication, we can treat it like a number without decimals and then reason where that decimal would go to make sense. So you might consider pausing the video and just trying this one on your own and think of what that would sound like to use reasoning and estimation to multiply it and place the decimal to go through. Now, what about division of decimals? What if we had that? Can you go ahead and try that again? Like if you haven't done this in a while, which you probably haven't. We don't divide decimals by hand too often in everyday life. But like, how would we go about doing something like that? What would that be? Try it out. What would you do there? We'll come back to that. But let's start with one that's just a little bit more basic here. Let's start with 1 8/10 divided by 4/10. And let's start with a context. Blake had 1 8/10 pounds of flour. Each batch of muffins needed 4/10 pounds of flour. How many batches could he make? Yeah, so what do you think? How many batches could he make? We could start with some estimation to go through that. And let's think about what this would look like in terms of a model for decimal division, and to think about the algorithm as well. So let's pull this back up here. All right, to this one. Oh, right here. There we go. All right. So we had 1 8/10 pounds of flour, or 4/10 pounds for each batch. So how many batches? So let's go back, and again, we could do different things, but I could have this be a whole again. So the question here is, what would this hole be? Well, that hole could be 1 pound of flour, right, to go through. And to make a key then what would this piece be? That piece would be 1/10 of that, so 1/10 of a pound. And if I end up needing it, I don't think I will, but if I end up needing it, one of the small cubes, would actually be 1/100th of a pound of flour. So here we have a key, which is good to think about and define clearly when using any manipulative. So let's start with our flour. What did we have? Well, we had 1 8/10. So if I got a bunch of these out here, 4, 5, 6, 7, 8, right? This would represent our 1 8/10 pounds of flour. So let's draw that out. So that's where we start with 1 8/10, 2, 3, 4, 5, 6, 7, 8. Now we want to see how many batches of muffins we can make, and we know that each batch took 4/10. So it's the same as before. How many groups of 4/10 can you make out of 1.8? Well, let's see. There's one batch right there, right? And, I can make another one right there. So that's a second batch. But what would I do with this one here? Well, again, I could trade it in. I could make a trade, and that here could represent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of our tenths. And if we keep doing it, I have enough for a third batch of muffins. Here's another for a fourth batch. But I don't have enough for a fifth batch. But how much of a batch does that represent? Well, I have 2 of the 4 I would need, so that would be a half batch in thinking of the context. So 1, 2, 3, 4 full batches of muffins and a half batch here. So the answer should be 4.5 batches of muffins going in. And so let's take a look and see how the algorithm allows us to see that as well. We started with 1.8 pounds of flour, and we wanted to divide by 4/10. As always, there's many ways to do this, but let me share one common way that is often done, a way we can make sense of it here. What makes this hard is, what are we going to do with the decimal places? Do we have to do something with them or go through? It'd be a lot easier. It'd be a lot easier if we didn't have a decimal out here. And so that's where the main algorithm that we often learn stems from, is to basically get rid of the decimal out here. And often you hear this. It says, well, out here, if I move this over one space to the right, I can do that as long as I move this over one space to the right. And that means that this problem should be equivalent to 18 divided by 4. But again, what's happening there? Why can we just, if we move it 1 here, why 1 there? Well, let's think. Going back, what this problem looks like as a fraction would be 1.8 divided by 0.4. And to get rid of a decimal place like that, to move it over, is basically multiplying by 10. That's how the decimal system works. And so what we really did there is, it goes back to our old friend, the giant 1. What we really did is multiply each of those by 10, giving us 18 divided by 4. And we know that when we multiply by a giant 1, the answer doesn't change, right? Multiplying by 1 doesn't change anything. So this decimal division must have the same answer as this one. They're equivalent. They have the same. Which means I can go over here and look at this one, and I don't need to worry about moving the decimal place back. I don't need to, because this is the equivalent. These two are equivalent. So now I can just worry about this. 4 goes into 18 4 times, and I have 2 left. Oh, but again, I have nothing more, but that's okay, because we can just go to smaller pieces here. And that decimal place here in division is always going to end up in the same spot, so I might as well move it up now. And again, I'm going to just trade in 4/10. So this is 20/10 now. So shared equally amongst 4 groups would give me 5 groups. And, that's nice. I didn't need to bring down the next one. And so we see again, we get the same answer. So again, we don't need to move a decimal place back or anything, because that was equivalent to that in the beginning there. All right, well, so that's decimal division, and we will have a chance to play with that a bit this week. So I want to end with the last section a little bit just on percents. We're not going to be able to do everything with percents, but just a little bit of thinking about of moving from decimals to percents and that connection here. So, true story here. When one of my daughters was 8, she received a coupon in the mail from a local store you may have heard of called Justice that often markets to young females. And she knew that this coupon was a good thing. 40% off was good, but she turned to me and said, "What exactly does 40% off mean anyway? What does it mean to you? How do you explain to someone what 40% off would mean?" Right? So we can think about it in different ways. 40% off, we might think about, well, first it might help to define a whole, to realize what does 100% mean? Right? 100% would mean to pay everything. So 40% off, well, we might think about a benchmark. So 50% off, that's half of 100, is half price, right? So 40% is, a little less than half. So we're going to pay here, we're getting what off? We're getting a little less than half off would be a way to think about it. We also think about it in terms of, how much of a dollar? What does 40% mean? It means 40 out of 100. So, for every $100 spent, you save 40, or for every dollar spent, you save 40 cents. Well, it really goes back to the definition of percent. Now, what is the meaning of that word? Well, if you break it up into the two parts, per and cent, per means out of, and cent means 100. So literally, percent means out of 100, which is what hundredths mean. And this is the big connection here, that percents is another name for hundredths, right? They're the exact same thing. When we have a fraction that's out of 100, or a decimal of hundredths, percents are just an efficient way of writing the same thing. So here we see the equivalent nature of the fraction to the decimal to the percent. All are the same, all just get used in different ways and some different purposes, but they're all interchangeable in different ways, and that's a big idea. Percent is another name for hundredths. 23 hundredths is the exact same as 23%. So let's go and just take a look at a couple of questions here. What's your method for finding percents? Like, let's take a situation here where a dinner bill was $62, and say your group left an 18% tip. Go ahead for a second. What's your go-to method? How would you go about and solve that? So let's just take a look and break this down for a little bit here. Obviously, we're trying to find 18% of 62. And so one thing is to use the meanings of percents. 18% is 18 hundredths. So let's swap it out for what we know. And so if you multiplied 0.18 times 62, well, that's because you just chose to swap out 18 hundredths. 18% for its real meaning, 18 hundredths. And if we multiply it out, we would get $11.16, right, would be the equivalent there. And so that's one way of thinking about it in terms of trying to make sense of 18%. Another really great way to do it, though, is using what's called a 1% strategy, and some of you may have done this. A 1% strategy is always asking, well, 18% is kind of hard to do, but 1% actually is a little bit easier to think about. Well, because what is 1% of any number? Well, 1%, again, means 100th. So to find 1% of anything, it's just dividing it by 100. With our decimal system, that ends up working out fairly nice, because 62 divided by 100 would just be moving a decimal left 2 spaces to get 0.62, or 62 hundredths. So that means I just found 1%, right? 1% of 62 is 62 hundredths. Well, that was easy to get when you think about it. To find 18%, I would just multiply 62 hundredths by 18. And look, I get the same thing as before, right? To go through. Now it's interesting, I get the same answer, but from that last method, you may notice that the decimal is kind of on the other number. That's okay, it just depends how we're thinking about it. Both make conceptual sense. This is just a 1% strategy and multiplying that 1% by 18. So let's take a look at another one here. Get a little visual here for percents. Often you'll see number lines, double number lines, bar methods. Again, we're not going to do them all, but just take a look at a couple here. So let's say a dress was $42 after a 30% discount. What was the original price of the dress? Can you pause the video for a second and see how you would solve that? What would the original price of the dress be? What's your method? How much you go about doing that? So let's pause for a second and try it out. All right. Well, again, using a visual bar method, we have to define our whole. Let's let this whole be the full price of the dress, 100%. So this represents 100%. And it could be a number line or a bar model. But we don't know what 100% of the dress price was. We know that's what we're trying to figure out. That's what we'd like to know. What we do know is that you got a 30% discount. And it's always helpful to think about, if you had a 30% discount, that means you paid 70%, right? So we paid that amount, that $42. And so if we think about it here, if we divide that bar up into, groups of 10, since into 10%, we now realize that, that 70% would be the first 7 blocks over there, these first 7 right here. And so we have to split $42 between these 7 chunks, right? What's 42 divided by 7? Oops, that would be 6, right? So each of these here would be 6, these 7. So, well, that means that these are also 6. That means we saved $18. And so any way we do it, we should end up getting 6 times 10 is $60. So the original price was $60, looking at a visual like that. Now, we could do the same problem using that 1% method. Let's think about what that would look like with a 1% method. Now with this one, it's interesting because we don't know what 100% was of the price. What does $42 represent? That's not 100%. Right, that would be 70%. And there's the key thought to begin with. $42 represents 70% of the original price. So to get 1% of the original price, well, we just need to divide 42 by 70, right? If we divide each of these by 70, and again, calculators can be okay here, that would give me 1% of the original, right? I'm just dividing each of those by 7. So if we do that, that would give me that 60 cents equals 1% of the original. And once I realize that, well, to get 100%, I would just multiply each by 100, and that would give me $60 would be 100% of the original. So if you think about it, it's again just using some reasoning here to think about a different way to make sense of a problem like that to go through. Yeah, so why don't you try one for a second? Can you take this one and see what you can do? See if you can go ahead and think out what a bar model might look like, what a 1% model might look like, and any third method. So why don't you pause the video for a second and just play with that for a second. See what you can do on your own at first and try those two on your own. I'll give you a second. Okay, well, let's take a look. This is our last problem, I think, of the day. It's been a longer video, so thanks for hanging in there. So it was $34 after a 15% discount. So if we were to use a bar model or number line type structure, we could think about this being, again, 100%, kind of the full price here. And we know that we got a 15% discount. So if I want to break it into groups of 10 to get 10%, I might do that. So each of these would represent 10% discount. So what would a 15% discount look like? Well, I guess it would be kind of half of that, right? So this here would be 5%, and this here would be would be the 10%, right? So what's left here? Then all of this represents 85%. And we can use different ways here. This one, you could think about it. If we wanted to think about it, what we might do is, since this is a half here, I could think about dividing these all into 5% pieces, right? So smaller pieces here, and realize that would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 5% pieces there that I need to split up that $34. So 34 cut into 17 pieces would be $2. So each of these 5% pieces would be $2. Yeah. So again, going over here, we know that this 5% here would be $2, and that means 10% would be $4. So ultimately, we saved $6. So altogether, if we put that in there, 34 plus 6 should be $40. Looking at that, right? And if we wanted to look at that 1% strategy, we would know that when you paid $34, that means that you paid 85% of the original price to go through there. Yeah. So if we were to use a 1% strategy, we'd want to basically figure out what 1% of the original price was. So to get from there to there, we would have to divide by 85. So over here, we would have to divide by 85 as well. And when we do that, we get 4/10 or 40 cents to look at it. 40 cents would be 1%. Since our goal is to get 100% of the price, we would multiply each of those times 100, and that would give us back to $40 is the same as 100%. And so again, just looking at lots of ways to think about it, but just trying to up our ability to think about this in different ways as teachers here. So that's the end here. So in this week's problem set, you're going to be playing with some of these different models and thinking about them. And I think a big idea here to end with is just, again, we're just trying to go back and not focus on just getting the right answer all the time, but focusing on why does that answer make sense? What visuals, what contexts, what ways, what reasoning strategies can we use to make sense of it so that over the long term, we have a better sense of how to be flexible in our thinking, how to approach problems, because if we only have a procedural knowledge, man,